şey yapabilirsin tabii, buyur. Yani Türkçe tanıtım aynı, problem değil. Ben tanıtayım hocamızı, çünkü ben davet ettiğim için şimdi ayıp olmasın. Şimdi Özgür hocamız benim çok sevdiğim bir hocadır. Kendisini epey yıllardır tanıyorum. E, Amerika'da tahsil yaptı, değil mi? New York'da. Sonra Rutgers'tan doktorası var. Transportation üzerine, ama aynı zamanda Soul Structure Interaction çalışmış hocamız doktorada. Şimdi de İstanbul Üniversitesi Cerrahpaşa kampusunda transportation üzerine ve daha ziyade railway transportation and the mechanics of railway transportation. Not just the planning or other means of transportation systems, but he's heavily involved in mechanics of the rails, the interaction between the rails and the cars, the foundations, of course, and all that. So he has developed some sort of theories, formulas. So he's very much involved in this sector. So perhaps he can tell us better about himself, but this is all I know. But I'm really glad that he accepted my invitation. And we're glad to have you here, Professor Bezgin. So the floor is yours. Please feel free. You can perhaps talk about yourself a little bit more, and then we'll go from there.
Thank you for this kind introduction, Professor Yalçın. It's a pleasure being here. Thank you for your invitation. I am actually a student of physics, following my education in physics in Hacettepe University in the 1990s. I transferred to civil engineering, Department of Polytechnic University in New York. After that, I was mainly interested in classical mechanics when I was in physics, so I moved on to studying structural engineering during my master's years, and soil and structure interaction and geotechnical engineering in my PhD studies. After that, after I finished my PhD, I worked in the industry for 7 years, where I was involved in both in geotechnical consultancy and also concrete prefabrication. So I applied the notion of soil and structure interaction within many fields, I would like to say. And actually, during my years in the prefabrication industry here in Istanbul, that's when I was exposed to railway engineering. And today, my main topic of study is railway mechanics and the dynamics of railway machinery and the response of the railway tracks to those impacts. Now, today's discussion, following this invitation, I looked back at my years in the prefabrication industry, and I wanted to speak about some current and some, I think, urgent topics. And seismicity was one topic that I wanted to discuss, because throughout my years in the prefabricated construction industry, this was one major field that I was involved in. And I would like to say that the topics of mechanics, they are not far away from each other. Unfortunately, sometimes in our country, the discussions for civil engineering or the topics of civil engineering are discussed as if they are totally separate and totally different from one another. But I think we sometimes forget the fact that they're all bound together by the laws of classical mechanics. And I think that understanding of those fundamentals is an important issue. And ever since I have known myself, I try to advance and I try to understand more into what's going on around me, and also what we do or what we don't do or what we need to do, or the way we do things today, but how we should do them tomorrow. I always try to understand and keep refining my understanding. And this is one thing that I would like to recommend to the students in my audience today. So thank you for your attendance. Thank you for being here. And thank you for giving me the opportunity to speak before you. So today's topic will be an insight into seismicity, prefabrication, and ductility. An understanding of seismic behavior, I would like to begin by that, followed by the prefabricated construction and connections. What type or what is the understanding behind prefabricated construction and connections? It won't be a too detailed discussion. I don't have time to do that, but I would like it to be somewhat a qualitative understanding. I value that a lot, qualitative understanding. Numerical understanding and numerical studies come later, but I think that the qualitative understanding is very much important. And I would like to end today's discussion by ductility, discussing ductility as a fundamental concept in structural design. So when we think about seismicity, we have to take the object of Earth that we live on, and it's how it's constituted, what type of an elemental character it has. And I think it's a very interesting object. It is a machine, actually. The more I think, the more I read about it, the more I think about it, I think of it more as a machine, a life-giving machine, a life-generating machine. It has a solid core, solid metallic core, surrounded by a liquid metallic surrounding. And then that is in return surrounded by a what we call as a lower mantle, which is molten rock, and an upper mantle, which is also molten rock, but with a higher viscosity. And then comes the crust, and which is the thinnest part of this planet. And it's a machine, actually, because all the dynamics that occur within this machine actually give the life on this earth. That's what we owe our life to. If this engine stops, life stops. The generation of the magnetic field, the generation of constant replenishments. Like when we think about earthquakes, we think about it as a bad thing, but it's actually a good thing in the way that the crust is always replenished. Old crust goes in, new crust comes out. Old crust goes in, new crust comes out. And this is like a never-ending mechanism inside until the earth cools out. And it does cool out. Like every time a volcano spurts out or it loses temperature little by little, quite little. I mean, for all practical purposes, we can say that it's a never-ending situation. And it is composed of 5 layers. And some interesting statistical facts is that the temperature increases about 25 centigrade degrees per kilometer that we dig in. And about 30 megapascal is the pressure increase per kilometer as we dig down. So these are some interesting numbers that I looked up as I was creating a class session years ago. So this is the fundamental quality of it. And we owe that a lot to that. And if you take a look at it from a rheological point of view, it is composed of 3 layers: lithosphere, asthenosphere, and mesosphere. And this is quite important because what goes on in the asthenosphere and mesosphere is actually the cause of what we are facing today. Because the solid part of this earth is actually a very quite limited part of it. And all the action that goes on the solid part is due to some reasons that goes underneath. Now, what is earthquakes? It's a rapid releases of mechanical energy that generates earthquakes. It's a rapid release of mechanical energy. It has to do with power, right? Power is the rate of change of energy with time, right? Rate of dissipation of energy or rate of generation of energy. If it happens slowly, nothing happens. The same amount of energy can come up, but if it happens along a long period of time, we don't maybe we don't even feel it sometimes, right? But if that energy is released rapidly, that causes, in railway engineering, it causes dynamic impact forces. In seismology, it creates earthquakes. But the fundamental concept actually is quite similar. And it's studied under seismology. It has been noted to occur up to depths of 660 kilometers. The deepest ones have occurred up to that depth, and we don't have that anywhere beyond that because it needs actually solid elements for seismicity to happen, because if it is malleable, if it's deformable, you don't have that solid body to store potential energy. It's like if it's like a spring, right? If it's a spring analogy, it needs to be solid, and the the solid content of the earth is not that much. All right. So the deepest ones, and these are quite low in number, has been noted to occur up to a depth of 660 kilometers, and there's nothing more beyond that. So why am I saying this? Because the radius is about 6,400 kilometers, and the earthquakes are generated within this initial 690 kilometers or so. And the majority of it is actually happening within the first 200 kilometers. So this is a very surface situation, actually, but a massive one. So the earthquakes actually can happen to many reasons. What we will be talking about, what I will be referring to today, will be the tectonic earthquakes, but there are other forms of earthquakes. This energy can be released in other ways, but the tectonic ones are the ones that we are interested in today. So the theory of continental drift proposed by Taylor and Wegener, this, of course, was proposed by them, but the mechanism was not proposed. Why are we drifting? Why have this drifted? It's because something must be pushing it, pulling it, dragging it. But one part of the story was known, certainly like pieces of a jigsaw puzzle. They were together at one point, and then they drifted away. But at some point they can meet again. They will likely meet again because, again, this process is not stopping. Now, the theory of continental drift in the beginning only considered the continental plates, because at the time we didn't have much methods to analyze what goes on below the oceans, right? I mean, we see the ground, but we don't see the bottom of the ocean. So we say, okay, nothing is happening there, but that's not the case. The theory of the plate tectonics was then improved to include the oceanic plates as well. So at the end, actually, the puzzle is not only composed of continental plates, but also oceanic plates. And 6 continental oceanic plates and 14 subcontinental plates make up this full spectrum. So this gives us a better understanding. This gives us a much better understanding of what's going on. Now, the plate tectonic theory is a kinematic theory, such that the theory considers the movement of the objects place and the variation of this movement in time, and not the driving force that causes these movements, right? Mechanics is a composure of statics, dynamics, and kinematics. Now, when we are talking about kinematics, we are only interested in the qualities that relate to motion. What is the speed? What is the position? What is the speed? What is the acceleration? Things like that. But when we are talking about statics and dynamics, we are interested in the forces causing or not causing those motions, all right? So there must be a mechanism within the earth. I mean, why are they moving all over the place anyway, right? There must be a mechanism. So one question leads to another, it leads to a research program and the whole scientific methodology. And the discussion concluded by stating that there's a thermomechanical equilibrium within the semi-molten rock. Warm material rises up, dense material sinks down. So it's like 2 tigers, equal in strength, locked in a cage, engaged in a never-ending fight. That was my response to when I first learned about this. So the theory of thermodynamics, the flow is from the hotter parts to the higher heat domain to the lower heat domain, right? So the flow is from within the earth towards the outside of the earth, but yet when something cools down, it becomes denser. So what becomes denser should sink. So there is a constant flow of material from the regions close to the center of the earth towards the surface of the earth. But as this material comes close to the surface of the earth, it cools down and sinks down, only to become hotter again and then start flowing towards the surface of the earth. So these currents, of course, this is in chaotic nature. It does have an organized form of chaos. I mean, this is a very basic depiction of it. But what happens is that the crust at the top is constantly played around with from the bottom. Something is rubbing to this crust at the bottom. So something is pushing it, something is pulling it, something is dragging this crust at its bottom. And it's called by these convection currents. This never-ending fight between those two tigers causing the material to flow from the hot region to the cool region, and the flow of the denser element towards the sinking of the denser element as it cools down towards the bottom. So this is the mechanism. This is the machine actually that's causing this movement. So this ongoing cyclic motion drags the upper mantle and thereby causing the plate tectonics. Shallow earthquakes, those that occur up to a depth of 70 kilometers, constitute about 75% of the energy released by the total amount of earthquakes. This is quite significant. And the closer it is to the surface, of course, it's like the closer the bomb explodes closer to you, the more damage it causes, right? The deeper it is, well, it is better thing actually. Deep earthquakes occur within the deep crust and mostly the upper mantle up to a depth of about 700 kilometers. So we have the plate boundaries, okay? So I would like to be careful about using, the plate has broken. Nothing is being broken. The plate, the boundary is there. It is a notion of the slippage along that boundary. So let's call it plate slipping rather than plate breaking. Sometimes in Turkish we say levha kırılması. Nothing is being broken. Levha kayıyor. Within that boundary, the plates slip. But of course, this is not a very smooth type of slip. It is not like those boundaries are oiled. There are some boundaries like that. Actually, there are certain boundaries where the two plates just move with respect to each other, but they don't store that much energy because the friction is low. So not all the slippage causes earthquakes, but most of them do, because there's this interlocking. And you can test it in anything. Like, there's an interlocking, you push it, you pull it, and up to a certain level, it just slips, something snaps, something cracks. And then that releases the potential energy that has been stored within. That's what's happening. So the seismicities are all correlated with these plate boundaries where the motions are occurring, okay? And so also the deep ones, shallow seismicity, deep seismicity, right? It's a very nice figure. I really like these figures. So these are quite instructive. And this is the famous ring of fire in the Pacific. Now, what types of motions do we have? So, okay, they are moving, we get that. So, well, how can they move? Well, there's actually three types. One of them is a spreading ridge boundary. This is actually the nicest one. This is something we have in the Atlantic Ocean. Right in the middle of Atlantic, there is this ridge where new material keeps coming out. So as it keeps coming out, it pushes the other plates. But of course, what comes up should go down. As this is coming up, it's pushing the other one down, and this is what's happening, especially in these territories. For example, the coast of Alaska, the coast of Chile, for example, subduction zones. The plate is going underneath another plate. This is the heaviest type of action going on. This is the heaviest type of deformation, heaviest type of forces involved. Something is trying to go underneath another thing. This is quite heavy. And there's, of course, the struck slip type of faults where two faults are sliding past each other, and they are like basically interlocking to each other, like the tooth of two chainsaws going in opposite directions. Depending on how well they are touching each other, that determines the intensity of the earthquakes. And this is what we have in our country. Now, this was a photograph that I took from my National Geographic at the time. I was in the United States. I was 22 years old. This was the edition when the earthquake happened in that year, and I was terribly upset. And I was a student of civil engineering. I was young, and I took this picture. I took that picture with the idea that one day I will be using this picture when I teach, and hoping that this never will happen again. Because the causes of earthquakes is known. It is like the winds. Okay, we are living in a physical object. This physical object has certain qualities, and we need to deal with it. So when the rain comes, you fix your roof so that the rainwater doesn't come in. When the wind blows, you do what you need to do so that the doors won't open up or the building won't collapse. Or your tent doesn't blow away, You do what you need to do. You respond to it mechanically, and such is the earthquakes. But the bad thing about earthquakes is that they occur rarely compared to our lifetimes. So a human life is, say, 80 years. How many times can a human face an earthquake, right? Once, twice, 3 times, big ones, right? So it doesn't, and we have a short memory. We are like fish. We have a short memory. We forget. We like to forget easily, especially if we have a responsibility or if there's a heavy working that we need to do. We try to forget things immediately. And this is what happens. Now, this last earthquake has troubled me in many, many ways. And I, for one, am the lucky ones. I was not directly affected by it, but I could have. And the fact that I wasn't affected is not, does not mean that I'm tremendously sad about it and tremendously angry about it, because the same thing happened this time in this region. And we knew that was going to happen. It was coming, but we ignored. So we need to understand this picture. Like, earthquakes is not like a punishment of God or something like that. You know, this is a bad understanding. There is not some big deity like throwing stones at us or throwing lightning bolts at us, something like that. It has nothing to do like that with that. Long times ago, when people didn't have science and didn't have means to understand, they thought that, Zeus was angry, sitting on top of Mount Olympus, and was throwing lightnings to us. But that was thousands of years ago. At today's day and age, if we think that, oh, God is angry with us, then we are just stupid. Simple as that. So this is something we may not need to, we don't need to know when it's going to happen, today, tomorrow, next year. This is a very stupid question to ask. And when I listen to the people speaking on the televisions, the ones I respect always say this: don't ask me when it's going to happen. It will happen. And when it happens, it's going to generate this type of a force. You need to do what you need to do to construct, to resist against this. Simple as that. If somebody is playing all this magician kind of thing, this is going to happen, how it's going to happen, that is just misleading. But let us just understand that this is nothing but pure mechanical situation that we need to understand as humans through the use of science. The answer does not lie in any other place. It lies in science, okay? Simple as that. So we need to understand this. We need to understand this very well, and we need to be observant of this fact. So this is what's happening. So our Anatolian plate is basically stuck in the middle between the Arabian plate and the Eurasian plate. It's like between the index finger and the thumb, we have this Anatolian plates. And this is what happened. The East Anatolian fault slipped down, Arabian plate pushed up, and this is where we got our biggest hits, and losing 50,000 people at this day and age to this horrible earthquake. And especially those structures that were constructed in the fertile agricultural soils was quite badly affected. There is a lot to talk, but I will try to keep my focus on and carry on. So the friction at the interface, we have two forces pressing us. So if the left piece was to slide past the right piece, it has to overcome this friction, which is related to the amount of pressure applied and also the friction qualities at the interface. So depending on how much this friction is, or how big these forces are, and how big this convection currents to slide these plates are, the seismicity is affected proportionally. So again, the subducting zones generate the highest amount of earthquakes, because once this one slips, so much stress are generated that the release of energy is greater. So actually, there are much bigger earthquakes than the ones actually happening in our lands. And the earthquakes that are 10 times or 100 times the magnitude, yet causing no loss of life, right? So we need to be observant of this fact. Earthquakes 8.5, sometimes 9 are hitting regions as dense as we are. And the damage and the loss of life is much less. Why is that? Why is that? So the local regions of the seismicity are the faults, and these faults slip past each other. So it's like it's not fault breakage, but fault slippage. This is the term that I prefer using. And there is the epicenter, which is the projection of the location of the fault, which is the hypocenter. And then the generated energy is spread around like as waves. So there's a very good book by Bruce Bolt, Earthquakes. I would highly recommend it. I had a Turkish copy by TÜBİTAK. It's a very good read, very fundamental, very wonderful book. I cannot recommend it enough. So when the ductile rock actually moves, it just changes form. So ductility here is also in play. So if it's a brittle formation, which it typically is, then this release is just instant and the damage is instant. But if it's a ductile breakage, it doesn't break. It just yields away and it releases the energy as it yields, as opposed to releasing the energy when it fails in a brittle manner. So this fundamental concept, you see this everywhere in the pencil that you hold in your hand, and deep within the earth, the concept is there. This is the beauty of classical mechanics. So I'd like to pass some of the slides to make better use of the time. So the types of waves generated are actually four fundamental waves: the P waves, S waves, we all know, and then the Love and Rayleigh waves at the surface. So these are the ones actually that generate quite a lot of damage, especially in soft soil, because this energy, this big amount of energy, when it dissipates into a weak territory, well, what is it going to do? It's going to generate a tremendous amount of shaking, right? As opposed to if this energy is released into a very stiff environment like rock, the amplitudes will not be as high. This is just simple reasoning. Simple reasoning. If you shake, for example, a brick, right, a box of brick, if you shake the box of brick, nothing is going to happen. But if you shake a box of yogurt, right, it's going to shake violently. And this is what's happening. And this is one of the reasons why not to construct in fertile grounds. Okay, but of course, construction is easy in soft soil. You can dig easier. Everything is easy, right? It is very difficult to dig into rock, but this is what you should do. So the understanding is sometimes, yes, maybe we are not going to live forever, but when we do live, we would like to live in a safe and a happy way. We did not come to this earth to die, right? So whenever you try to do something that lasts, sometimes the society reacts different ways. Why are you doing this? Are you going to live forever? No, maybe not. But yes, when I do live, I would like to live a very happy and a healthy being. So this is something, this whole things are interrelated in a way that we cannot fathom, we cannot imagine. Sometimes the response of the society to this, the way we understand it, and sometimes the way we try to understand it in order to, keep the blame away from those that need to be blamed, is giving us the true damage. Because I, for one, experiencing the same thing twice in my life with 20-year intervals is quite heartbreaking. And I, for one, feel the need to do something about it. And I do not have any more fear with respect to anything else. So I'm speaking freely and I'm talking about these things freely. So the wave speeds, they are introduced by material properties, the speed of the way it goes into molten material and the way it dissipates in the solid material. It is quite interesting. So for those of you who are interested, these are some of the headlines that I would like to put out there. The time is perhaps not known, but the location is known. And when it does happen, what the magnitude will be is also known. So the question is asked that whether we are prepared for it or not, because sometimes it turns into a gamble. Like, hey, if it's going to happen in 10 years, I'm going to construct accordingly. But if it's not going to happen in 50 years, I will construct accordingly. This type of morality cannot exist. Okay. So depending on if it will happen, I'm going to put more steel. If it's not going to happen, I'm not going to. This is wrong. This is wrong. And it must be screened that it's wrong in every field. Asking when it's going to happen is, and of course, the media is always interested in these types of actionable news, right? If you talk about some sane and calm attitude matters, nobody is interested. But if you talk about blood and loss and this and that, all the media is onto you. But especially, for people who are teaching this, it is essential that, we need to always keep our concentration on the truth. When it's going to happen is not an issue. The issue is that we need to be prepared to what is going to happen. And we need to construct it accordingly. At this point, Professor Yalçın, we have 1 minute to go. So my suggestion is perhaps we can stop here and then restart. Would you agree?
Exactly.
Okay.
As I wrote in my in the chat, we can stop the meeting now and then sort of restart with the same address, Zoom address. Okay.
Okay, let's do that. So I'm
And then
starting.
I'll turn the host over to you later on.
Okay. Thank you. So I'm stopping and ending the conference session right now. Thank you.